So this should be fresh, right? Just did it 30-1, really fresh. So review of exponential and logarithmic functions. So an exponential function is of the form y equals b to the x. The point being that the variable is in the exponent, right? Where b is greater than 0. Graph of y equals b to the x, where b is greater than 1 is shown below, right? So like 2 to the x, 3 to the x, whatever. Graph of y equals b to the x, where b is between 0 and 1, right? It's got to be greater than 0, right? So a half to the x, a third to the x. Okay. So using these graphs, let's complete the following limits. As the limit of b of x as x approaches 0 is 1. The limit of b of x as x approaches infinity is infinity, yeah. And the limit as x approaches negative infinity of b to the x is 0. Correct. So that's when b is greater than 1. When b is between 0 and 1, then this limit is, first limit, 1. As we approach infinity,
0.
You see it going down further than I see it going down. And as we approach negative infinity,
Frantic pointing?
frantic pointing, yes, to infinity, but not beyond. Please the following table. So the domain of an exponential function is that, what? Set of all x such that well, in the interest of getting through the lesson, x belongs to the reals. Yeah, you can put anything up there for an exponent. Positive, negative, doesn't matter. Heck, look at the diagram. You can see the x is going both ways forever. Or negative infinity to infinity, right? The range.
Y is greater than 0.
Thank you. Or using the bracket notation or whatever the name for that notation is, 0 to infinity. X-intercepts.
There aren't any.
There aren't any. Y-intercept.
1 for 1.
Is that how many or what it is?
Wait.
Oh.
Both. Good. Yeah. Horizontal asymptote.
Wait, 0.
Y equals 0. Excellent. State. State. Don't got to show no work. Yeah, it's a double negative. State the limit. State the value of each limit. The limit as x approaches 4 of 3 to the x minus 4 is. Yeah, it's in existence, right? It exists, so we could just say, well, okay, it's. Whoops. We just say that's equal to 3 to the 4 minus 4, which is 3 to the 0 or 1. The limit as x approaches 0 from above of 4 to the 1 over x. Infinity, so how'd you come up with that?
Because it's a 0, or it's 1 over 0 at that point, and so you take numbers that are very close to 0 on either side, which creates an infinitely large number the closer you get to 0.
And 4 to the power of an infinitely large number is?
Bigger.
It's actually, I think, the same size as infinity. So we could think of this as 4 to a large positive number. Okay, so that's how you can think of it. And that's equal to infinity. Now, another way you could do this is to say, well, let's let t equal 1 over x. Right? And then we can say, well, as x approaches 0, what happens to t? T approaches infinity, right? And then we're looking at the limit as t approaches infinity. Not very well written. The limit as t approaches infinity of 4 to the t, which is going to be infinity. Okay. Now, since it says state, I mean, either one is, quite acceptable, right? You just say, well, it's 1 over x, and it's 0 from above, so it's a very small positive number. 1 over very small positive is a very large positive number, and away we go. So, you do C using the same reasoning, but approaching 0 from below. And do both write-offs, right? Like, just think about, okay, what's it going to be, right? If I do this, but I've got 0 from below. Okay, so does that match up with your thinking? So we know that like 4 to the negative 1 is a quarter, right? 4 to the negative 2 is 1/16. 4 to the negative 3 is 1/64. 4 to the negative 4 is 1/256. Getting smaller. So 4 to a really large negative number is going to be 0.
Right, 1 over infinity.
And then what?
Still kind of the same thing.
Okay, so it's the same thing. Let's just write 0. Go, write 0. Or your mark will be the correct answer. Okay, x approaches 3, which way? Is that below? 3 from below of 1/2 to the 1 over x plus 3. Okay, thinking about it, what do we got? Approaching 3 from below, so what's below 3? 2.9999999, right? Okay. Oh, is that negative 3? Forgive me, my eyes cannot resolve such things. Any of you become eye doctors? Resolution. Negative 3. Okay, where are we coming? Negative 3 from below. So negative 3.0000001. And when you add 3 to that, what do you get? A small negative number. So what's 1/2 to a small negative number? So it's positive 2 to a large, what is it? That's going to be, so 1/2 to a negative is going to be 2 to a large positive number, which would be infinity. Okay? So, the reasoning, 1/2 to a large negative number, we want to take the negative, right? So we make that 2 to a large positive number. We change this from negative to positive by flipping, right? So a large positive number, which is infinity. Okay, so equals, I guess. Or let t equal 1 over x plus 3 as x approaches negative 3 from below. I keep throwing inverses on there. Then what does t approach? Negative infinity, right? So the limit as t approaches negative infinity of 1/2 to the t is equal to positive infinity. Okay. Now, being as it says state, you can just go through the reasoning up here and give the answer, right? So you get a question that state the following limits, right? Logarithmic functions. What's the inverse of y equals 3 to the x in exponential form? Sorry, ready to turn your page. What do you do to get the inverse? What do you do with x and y?
Switch it.
Switch them. And changing that to logarithmic form, it becomes, yeah, well, let's write it as y equals log, 3 is the base, y is the exponent, right, and x is the thing, the value, I guess. So, look, it's right here. The inverse of y equals b to the x is y equals log base b, and you know that, right? You just spend a semester doing that stuff. The graph of y equals log base bx, where b is greater than 1, is shown below, and the graph y equals log base b of x, where b is between 0 and 1, is shown below here. And we want to do these limits. So the limit as x approaches infinity of log base b of x is thank you. And the limit as x approaches 0 from above of log base bx is, really, it looks to me like it's heading down, so negative infinity.
The x value will crush.
Yeah. Okay. It's all right. It's all right. Why we're here to learn. This guy, the limit as x approaches infinity of is
Infinity.
really, because I'm looking down, you're looking up.
Damn.
So would you care to change that?
No, I think I'll stick with it.
Okay. And the limit as x approaches 0 is, now you can use your last answer, right? Okay. Domain. Set of all x such that x is greater than 0 for, like so. The range, all real numbers, y belongs to the reals, or x-intercepts, 1. Y-intercept, none. Vertical asymptote, x equals 0. Okay, all good? It's all right. It's all right. State, again, state the value of each limit. Okay, again, we'll do them each couple ways, right? So one, just think x approaches 5 from above, I think, right? Yeah, good. Log base 2 of x minus 5, so it's log base 2 of what kind of a number? Very small. What? Very small, but what? Yeah, very small, but
Positive.
positive. Are you sure? I'm positive. Log base 2 of a small, right? Because you need to know, right? I mean, what if the log of a negative number? Doesn't exist, right? You got to know that, right? And some of these will be, hey, that doesn't exist, because you can't do that. Okay, and the log of a very small positive number is, look at the log curve, is very small positive number. On the curve, you're not looking at your curve. What kind of infinity?
Negative.
Yeah, the negative one. Okay, hey, look at the curve. It's sitting there, it's staring you in the face. Okay, or what can we do, right? Or let t equal x minus 5. As x approaches 5 from above, t approaches 0 from above, right? Because positive, right? Small positive number approaching 0 from above. And the limit as t approaches 0 from above of log base 2 of t is equal to negative infinity. right? I mean, just exactly what it says above, only you've got a 2 instead of a b and a t instead of an x. Okay, the limit as x approaches 4 from below. Log base 1/2, 4 minus x. Okay, so 4 from below. What's 4 minus a number that's very slightly smaller than 4?
A very small
A
positive.
very small positive number. So we've got log base 1/2 of a small positive number. Small. And what is the log? Base 1/2 of a small, not on my sheet, I can't scroll there. Positive infinity. Or what do we say? Let t equal 4 minus x. Then as x approaches 4 from below, what does t do? T approaches 0 from above, right? So what we're saying, right? This is just the way it's more formally stating small positive number, right? So we have what? The limit as t approaches 0 of log base 1/2, in this case the b value between 0 and 1 of t is equal to infinity. Three, state the domain of y equals log base 3 of 5 minus 2x. So what do we know about 5 minus 2x? Five minus 2x must be taking the log of something, and I can only take the log of
Positive.
positive numbers. So 5 minus 2x must be
Greater than 0.
greater than 0. So negative 2x must be greater than negative 5. So x must be less than 5/2. Okay, right? I have to tell you, when we divide by a negative sign, we reverse the inequality. Okay, turn the page, flip the booklet over. Actually, don't turn the page, flip the booklet over. Exponential and logarithmic expressions. Use the fact that y equals b to the x is equivalent to blah, blah, blah. So 2 cubed equals 8 in logarithmic form is log base 2 of 8 equals. Right? Okay. You do the next one. You don't even need to know anything to do the next one, really. I mean, there's only one way you can put those three numbers together to make a true statement, I think. Yeah. Only one way. You can't do 81 to the negative 4 equals. No, that wouldn't work.
So you need 1 over 81?
Oh, I do,
Or you can
yes.
take the negative from the 4, and it would be 81.
Yeah. You're right. My bad. I couldn't resolve the 1 over 8. It just looked like an 81 to me. Okay, not true. Evaluate. Okay, you do them, I'll do them, I'll give you a lead. They're all nice, easy numbers, right? No calculator necessary.
Multiply by 5 4 times.
It's like a review of, wait, that's what the unit was titled, a review of exponential and logarithmic.
Anytime.
It's like a review of.
Let's head start.
Okay, remind me when I count bodies to not count one. Not that he doesn't count,
No, but
he just doesn't count.
Yeah.
Okay, good. I always like this one, right? Laws of logs. Okay, we know this stuff, right? So the log of a product is equal to the of the log.
Christianity.
Yeah, sort of. It's recording. I can't tell that joke. All right, hang on. So the product of logs is the log of a product is the sum of the logs. Not all of the logs, some of the logs. Really? No one? The log of a quotient is the difference. Oops, I suppose I should at least put an X in there. And the log of a power is n times log base b. It's my favorite law, right? It allows you to solve for an unknown exponent, which before that we had to like graph it. Do stuff. Okay, expand this. Log base 3 of x squared y over 9z. Okay. Well, we got two things being multiplied and one being divided. So the things being multiplied, well, so let's take the log base 3 of x squared y minus the log base 3 of 9z. Right? So that's a difference. Let's throw some brackets around here just to show that we're serious. Okay, so that's equal to log base 3x squared. And then what? Well, it's a product, so that becomes a sum. I'm not going to wait for you guys. Minus, okay, we can show this here. So let's go minus log base 3 9 plus log base 3z. Now, I say that only because I put brackets around that expression, right? Which we're then going to remove and, clean things up a bit. So we take the power and we write 2 log 3x plus log 3y minus, what's log 3 9? 2. Minus log 3z. And there we go. We have taken a single expression and made a hash of it. A nice little compact thing. So let's take a 3 log 2 blah 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 and express that as a single logarithm. Okay. And I have faith. Okay, so we got to move the numbers, the coefficients out front have to be up there as powers, right? Because then we can apply the laws. You can't apply the law to like 3 log base 2x and 4. And then it's log x cubed, suckers on top, divided by y to the 4th, divided by z. And there we go. And one more, right? So applying the same methodology. Whoops. Uh, 6. Right, that's just a cell. Let's go 2 times 3, just in case. So what do we got? Log base 3 of 12. 6. Seven. Yes. Good times all around. the seemingly last page. However, you'll need to write down another page. We're just going to give you some examples of some of the stuff that was left example-less, lest you be left blowing in the wind during the 5 days you have to, get yourself caught up and all that good stuff. So remember, you got 5 days coming up, right? Chance to catch up, do a little bit of homework. Go back and do some early stuff too, right? Like fill in the blanks. Any of the stuff that wasn't assigned, you can go look at some of those questions, right? Because the last thing you want to do is hit the test whenever it is, and that stuff is like way far away and just sort of, has left your consciousness. Solve, express your answers in exact value. So, what do? Solve for an unknown exponent, you take the log of both sides, right? You then use some power. That's x log 5, not x equals log 5. And then write x equals. And that's your exact value, right? Now, if you're going to evaluate that, because this express answer is exact value, right? We're going to probably do more of that, because it's not going to ask you to evaluate a lot of stuff without a calculator. Hey, what's log 6 divided by log 5 without a calculator? It's like good luck. And I mean, if you have a fancy calculator, then you could just have taken this and gone straight to log base 5 of 6 equals x. Right. A fancy calculator where you can actually put the base in. If you remember how to do it, it's like you got to hit the alpha key. I think that's the key. Or not the alpha. Yeah. Second alpha, right? And that brings up the little menus and stuff. Yeah.
No, math alpha math.
Math alpha math? Okay. See, I don't even know. It's just easier to not worry about such technological marvels hidden in menu systems. Okay, what do we do here? Same thing. And we pull the power, right? But make sure that when you pull an expression down, that you put parentheses around it, right? Because it's that whole expression that's being brought down. It's not like 2x plus 3 log 4, which, would end up. And log 10 is just kind of 1. And so, we got to solve for x, right? Express your answers, exact value. What's x? Okay, so 2x plus 3 equals 1 over log 4. So 2x is equal to 3, and then x is equal to what did I mess up?
You could have just put log base 4 once, that's 0, and then you just put -3 and then the 2 over that with -3 half. You know what I mean? Like you just divide log 4, you get log base 4 1, so that's 0. And then you move to, so you got 2x plus 3 equals 0, then you move to -3.
I don't think so. Because it's not really a log 4.
Oh yeah, they both have to be log 2 then.
It's like 2. It's like 2x. I mean, another way to do this, we could expand it out. So we could go like 2x log 4 plus 3 log 4 equals 1, and then go 2x log 4 equals 1 minus 3 log 4, and then x equals 1 minus 3 log 4 over 2 log 4. Yeah?
I'm really confused for like that question. Just go log base 4 or 2x plus 3 log base 4 10 and get 10 to connect to that one.
That's the answer you got.
Yeah.
Yeah, so I think that works. He's just doing it for the plebeian with garbage calculators.
Well, we're asking for an exact value as opposed to.
Well, but it is still an exact value. It's like log base 4 of 10.
Oh.
Yeah.
Oh, okay. So, or, where are we? Log base 4
Yeah,
of,
that's yeah.
and then,
X is equal to log base 4 minus 3 over 2.
right. All of the above.
But which one is most correct?
If we're sticking in base 10, this actually could probably be simplified, right? It would be like 1 minus 6 over 2 log 4.
No.
No?
3 has to be divided by 2.
Oh, wait. Yeah, hang on. So, 1 minus 3 over 2 log 4.
Minus 3 log 4.
Right. Oh, look. Use the change of base formula to evaluate log base 3 of 20. Yes, you can use your calculator, or if you don't have one, because you gave up on bringing them, unless you're doing physics or chemistry, right? In which case you would have one. All right, so if we say use the base change formula, you have to use the base change formula, right? So log base 3 of 20 is just equal to what? Log 20 over log 3? Which when evaluated on your calculator is 2.73. I'll pause. What is E? What is E? You guys haven't seen E yet, have you? Have you seen E?
I accidentally made it on my calculator. I was messing around and
Did
I
you?
accidentally.
Yeah, it's fun to get, right? Because there's a number of ways you can do it. Well, here's one. Not exactly. Use your graphing calculator to determine the value of each limit rounded to the nearest hundredth. Okay. I don't like graph. What is this graphing calculator? X, in this case, X, right? It's not going to use H. So as X approaches 0, what is the value? Yeah, so let's go with 0.69. So we say 0.69. Ooh, in red. What about for B equals 2.5? Let's go here. Whoops. Let's go here and type in 2.5. Okay, so now what is it? So we've got like 0.91. Okay, because the closest we're getting seems to be that negative 0.01. So let's go with 0.91. What about when B equals 3?
No, I guessed.
Yeah, it's okay, 3. Oh, come on. Delete. No, backspace, 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 3. And we get so like 1.09. No, wait, I was there. So here we go. Big statement. There exists a value so that the limit as h approaches 0 of b to the h minus 1 over h is equal to 1. We call this value E. That is, E is the value such that the limit as h approaches 0 of e to the h minus 1 over h is equal to 1. Determine the value of E rounded to the nearest hundredth. Okay, so you can play on your calculators with that. we can go here and I can slide the b. It's what we're looking for. What's too low? We're looking for is I want that to be a 1. Right? And yeah, too low. 2.4 is too low. But 3 is too high. Okay, it's not going to be easy.
No.
Okay, that's pretty close. Go closer out of 1. It's getting close to 1. It's not quite there, right? We want nearest 100, so we know, well, 2.7 is a good starting point then, right? So if you haul your calculator out and you go, what do you go? 2.7 to a really small number. Anyways, I'll give it to you. It's 2.72. If you're a little more accurate, then it's that. Okay, and it's like pi, it's one of these transcendental numbers. You just keep going forever. Alright, so that's E. And E is this number, right? It has that special property, such that the limit as h approaches 0 of E to the h minus 1 over h is equal to 1. Okay, what is ln x? The inverse of y equals e to the x is, what do you do to get the inverse?
The x and the y.
Yeah, so x equals e to the y. In logarithmic form, what does that become? Sorry, it's going to be y equals what? Log, what's the base? E of x. Another expression for log base e to the x is ln x, which is read as ln, or ln. If you happen to be a fan of the show, call it ln. Okay, mostly I'm going to say ln, right? Or sometimes ln, or natural log. Okay, so there's nothing unnatural about e. It's the base of the natural logarithm. It's important, right? Look on your calculator, right below log. What is that? ln. Okay, so it's got to be important. They actually devoted an entire key of the calculator to this function, right? So it's no, somebody made this decision. Hey, this is important. So we're going to give it its own key. So in other words, the exponential function y equals e to the x and the logarithmic function y equals ln x, right, which is log base e, where e is this special number such that the limit as h approaches 0 of e to the h minus 1 over h is equal to 1, right, special number, are inverses of each other. So let's sketch these graphs. So y equals e to the x is indistinguishable from y equals b to the x, where b is greater than 0, right? I mean, it's just, only the base is a little more than that, right? Clean that up. So that should just be going down. Okay, so there's y equals e to the x, y equals e to the x, and ln x is going to look a lot like log where b is greater than 1 of x, right? Which means we start down here and go up there. That's just the base is this 2.7 182818284590 4522526. And you can develop this through, it's interesting. Okay, let's do that. So let's say you have $1 in the bank. And the bank is going to be generous, and they're going to pay you 100% interest a year.
Invest more.
Right. Or you're sending me the loan shark and you charge 100% interest fee, which is actually low for No. Okay, the bank's going to pay you 100% interest a year, right? So $1 after 1 year is going to be worth how much? $2, right? If you compound the interest once a year. If you compound semi-annually, you're going to get paid interest twice a year, right? Now you're not going to get 100% twice a year. You'll get 50% the first half of the year and then 50% the second half of the year, right? And you'll have $2.25 then, right? Because you go from $1 to $1.50, that $1.50 will earn 50% interest, which is 75 cents. You'll have 2 1/4. Okay, what if you get paid annually? So 12 times a year. Well, that's going to be 100 divided by 12 to the power of 12, right? So you're going to have 1 times 1 plus 100 divided by 12 to the power of 12, which is, anyway, what if they paid you interest every millisecond of the year? So now you've got 1 plus 1 divided by a really large number to the power of a really large number. So is it going to be forever? Like, are you going to get like $20 million after 1 year because you're getting paid interest every millisecond? You're going to get $2.72. You're going to get E. The limit of natural growth. So there you go. That's E.
Oh, look, it's compounded.
Yeah, compounded. So if we compound it infinitely many times, it's just going to come out to the limit as x approaches infinity of 1 plus 1 over x to the x. Is E. Okay, so let's do some examples. Let's do some limits with ln and E, just so you got something to look at. So you need a piece of paper or somewhere to write or whatever, so you can print it off later. Up to you. Examples. Zing. The limit as x approaches infinity. Okay, so the limit is x approaches infinity of e to the x minus 1. So you're going to subtract 1 from infinity. And then take e to that power. So e to a really, really large number is going to be a really, 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 really large number. And then you add 2 to it, and so it becomes, yeah, it becomes 2 more than what it was. And that's just equal to infinity.
Should we write infinity plus 2 to be clear?
No, because to be clear, that's not defined. The limit as x approaches negative infinity of the same thing. So now what's happening?
E to the power of an extremely small number.
Yeah, you're taking e to the power of a very large negative number, which is 1 over e to a very large number, which is
pretty much 0.
0 plus 2.
2.
2. There you go. 2. 3. The limit as x approaches 3 of 1 over e to the x minus 3. So you get to 3. 3 minus 3 is 0. E to the 0 is 1. 1 divided by 1 is 1. Four. Limit as x approaches 3. One over x minus 3 squared. How does that differ from the previous one? It doesn't. Exactly. What are you doing? Well, we're going to take a really, really small number that's pretty much 0. And actually, it's continuous, isn't it? At 3. You do that. You go below 3, you got a problem. No, you don't. You just have to make no. So at 3, it's continuous, so the limit is just evaluating it right there. 5. We do like 13 of these maybe, I don't know, 5. Okay, limit as x approaches 3 from below of 1 over e to the root x minus 3 is. Does not exist. Why not? Because
You can't have a negative root, yo.
can't have a negative root. Okay, you're approaching 3 from below, like 2.9999 minus 3 is a small negative number. I'm trying to take the root of a negative number, and that won't work. Okay, how about this? 3 from above. Three from above minus 3 is going to be really small.
Negative.
And the root of really small, like 0 is 0, and e to the 0 is, and 1 over 1 is, yay. All right, now comes this question. But it's continuous at 3, right? You put a 3 in there. 3 minus 3 is 0. The root of 0 is 0. B to the 0 is 0. 1 over 1 is 0. So, okay, it comes down to this. We'll never ask you that, okay? And it's sort of the same discussion of this, right? What's the limit as x approaches 0 of root x? Well, so if we take limit as it's got to exist on both sides, because from the left it doesn't exist, from the right it does exist, right? And it's continuous, right? We might say, look, it's continuous, and therefore you can evaluate it there, and therefore it is 0, right? But then where he says, yeah, it exists from the right, it does not exist on the left. So it's kind of beyond the scope of the course, and I'm just going to, so this is off of mathstackexchange.com, and if you just Google it, you could find that. So here's where he says, look, the limit 0. 1 considers only x in the domain of f. People saying the limit doesn't exist seem not to have understood that concept. I think that's way too tight. It may be a matter of definitions. Not to be confused about the comments, please. Experienced people think about it because you know there's an expression. And we come down to this. From what I understand, this limit is in fact 0. I understand where your confusion comes from. If I understand correctly, you've been taught this, right? If you've been taught, then this will not exist. Both left and right side limits must exist. And other people basically saying the function isn't defined in the negative domain, and therefore by definition you cannot take the limit in that domain. Doesn't mean it doesn't exist. Anyways, discussion. That's for your second, third, or fourth year calculus courses, right? And this guy made dependent definitions. So it's really comes down to a tightening up of the definition of limit, which you're not going to, excuse me, which we're not going to deal with in Math 31, and you're not going to deal with in first year university either, right? Many introductory calculus books define this under this premise, blah, 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 right? Okay, so there's discussion. We won't ask you this on a test, so you don't have to worry about, do I put 0 or do I put does not exist? Okay, so for now, we'll say this. Anyway, I mean, you can see there's discussion about it, right? So not everything is nailed down, and at this level, that's definitely not nailed down.
Why would
Limit.
you show that to us?
Blame Dessens, it's her fault.
Okay, I'll go tell her that.
You tell her that.
So what are we supposed to say for that one?
We're not going to ask you that on a test, and there won't be anything in your textbook that asks that either.
Oh, okay.
Okay. Again, because it requires much further going into. Pretty sure you got to delve into like second, third, or fourth year calculus before you're going to get a text and say, hey, now, like remember I told you about the epsilon delta definition of limit and that. So again, we're not covering that here. The proof of the sine x over x is 1, relies on the squeeze theorem, which is on page 303. We're not covering it in this course, right? But you will see it in a first year course. Then you'll do the squeeze theorem and other sort of things. All right, limit as x approaches 2 from below of the ln of 4 minus x squared. So what's that going to be? The ln of a small positive, yeah, so when we're talking, a small, we have to say, right, small positive or small negative, right, because in this case it matters. So it's the ln of a small positive number, which is, looking back, you can put your booklets where you can actually see the ln function, and say small positive number is going to have a ln of negative infinity. So then, can you write the word ln? If x approaches 2 from above, we are going to have a 4 minus x squared is going to be a, yeah, the limit won't, but so 4 minus x squared is going to be a small negative number. You cannot take the ln, right? It's a logarithmic function. You cannot take the ln of a negative number. Okay, what do we got? 4 more. Limit as x approaches negative 2 from below I'm just going to hammer this ln of 4 minus x squared thing for a while. Okay, negative 2 from below. What's 4 minus x squared going to give you? A negative number, right? Negative 2 from below when squared is going to be bigger than 4. 4 minus bigger than 4 is small negative. Cannot take the ln of a negative. Oh, what could the next question possibly be? Yeah, negative 2 from the right of the ln of 4 minus x squared is negative infinity, right? What are we going to get? Well, okay, negative 2 from above is like negative 1.99999. Squared is less than 4. 4 minus a number less than 4 is a small positive number. And the ln of a small positive is negative infinity. And 2 more. 12. The limit as x approaches pi from below or from the left. Do you prefer left or below? Left? Okay. I may ignore your preferences. Okay, so as we approach, it makes more sense, I guess. So as we approach pi from the left, then sine of pi is going to be 0. So we're looking at the sine of 0, which is 0. Okay, now, is that 0 going to be a positive 0 or a negative 0? Well, you can't take the ln of a negative, yeah.
You also can't take the ln of 0.
But you can take the ln of a number really close to 0. But this is a number that, if you're approaching pi from the left, then you're approaching 0 from above. So you've got a ln of a really small positive number, which is negative infinity.
Excuse you. It's a spin graph. Tell them what it is.
Okay. One more. Okay, if you are approaching pi from the right, then the sign of that will be a small negative number, and the lawn of a small negative number does not exist.